Hi, welcome to the first session of week 7. As I had indicated during our sessions of last week, this is really a continuation. For all practical purposes, really all of these could be combined into, you could say, one session, week 6 and week 7. So what we're going to do today is really work out a numerical example based on the Hotling principle. That's to say, we have already looked at the way that we would allocate efficiently a certain quantity that we have if there is only one period. That is very simple. It's nothing else but supply is equal to demand, and obviously supply, as we all well know, is really the marginal cost. Then we said, what if we have two periods? If we have two periods, then we'll have to worry, if you still recall, and I hope that all of you do, we'll have to worry about the present value in that case. That's to say, we have to take into consideration the discount rate. And the problem arises only if the quantity that is available is less than adequate to meet the demand in the market for these two periods. Then, let's say, if we have 100 and the quantity demanded for each period would have been, say, 30, then in that case we don't have any problem of allocation over two periods. But what if we're going to become even more realistic and we say we have a particular quantity, which is always the case in all of these exhaustible resources, non-renewable resources, and we have to allocate it over n periods. How do we allocate it? Which is the best way of allocating it? Is there an optimum? And what we're suggesting is that yes, there is an optimum. So what I'm going to do today is, during this first session, I've already worked out a few examples, but I'm not going to bore you, obviously, with giving you more than one or two. I think we'll do maybe two quick examples. But you've got to pay attention and make sure that you can follow this and replicate it, because you are again going to be held responsible, obviously, for solving these quantitative problems. So let's recap again. You have a particular quantity, what we have referred to over time as being the static efficiency is no problem, because that is when you have the regular supply is equal to demand. When you have two periods, then you do have a problem if the quantity available is less than the quantity that would have been sufficient to meet the demand in each of these two periods, and the discount rate then becomes important. Over n period, it's really essentially the same principle. That's to say, the discount rate becomes important, but we've got to right now be able to resolve the problem. The unfortunate thing about it, as you'll find out in a second, is that to do it by hand, as what we're going to do, obviously, it really depends to a very large extent on a guess. That's to say, you have to get started, and you get started by making a guess. If that guess turns out to be too high, then you lower it. If it turns out to be too low, then you increase it. And you keep on moving towards that particular point that will satisfy the conditions. Now, what are the conditions? The condition, as you might already expect, is that, let's assume for the sake of the argument that we're starting with a particular quantity of 100, then we're going to allocate it over n periods, whereby the total sum of the allocations cannot exceed 100. Because if we have 100, we cannot allocate in order to consume 110. Where are we going to get the additional 10 from? That is the problem with oil. We cannot keep on having demand for oil that doesn't exist. The other thing is going to be the price. There is going to be a particular demand curve. We're going to assume that we have a demand curve, otherwise we wouldn't be able to move at all from square one. So given that demand curve, what will we be able to calculate? We will be able to calculate the maximum price that society is willing to pay for that particular commodity. So if I'm going to go ahead and allocate 100 units of something or another, and my maximum price, say for the sake of the argument, is 20, then I cannot assume that I'm going to wind up in having a price of 45 during the 15th period, because society is not willing to pay 45. So the conditions that need to be met for that optimum allocation over n periods is that I will have that particular quantity that must be totally allocated. It cannot be exceeded, the allocation, and the price must never go above the maximum price that society is willing to pay. And how do we find out, by the way, the maximum price? Given the demand curve, the maximum price is when the quantity is 0. So you know that you have optimum allocation, by the way, if you've noticed from what I've just said in the last few minutes. If it so happens that you've got to use the last drop available by paying that maximum price. You cannot pay more than the maximum price, and you cannot consume a negative quantity. So you cannot consume more than what you have, and you cannot pay more than the maximum price. Now, keeping these into taking all of these into consideration, let me see if I can right now share with you a few numerical examples. Let me start from the beginning by really stressing what is probably the single most important thing. We're gonna say, as we have said before, but let us just put it over here, that the price is equal to the marginal cost of extraction plus the rent. And in most textbooks, this is referred to as the MCU. MC sub U usually. So now notice what we're really saying. For the sake of solving our problems, I do not have to do that, but I'm going to assume this, and I might even do it on the exam. But even if I don't do it in exam, I ask you what is the difference. To simplify this, we can assume that marginal cost of extraction is 0. If marginal cost of extraction is 0, then what happens? Therefore, the price is equal to the rent. Now, what we're going to assume, which is assumed in most problems, is that, mathematically that is, we call the rent lambda. So let me assume, for the sake of the argument, that I have a demand curve. And what did I assume over here? That the price is equal to 20 minus 0.4 Q. And we're going to have to make an assumption about the interest rate. So let's assume that the interest rate, or the discount rate that we're going to use, is 10%. And let us assume that our margin, or we did assume that the marginal cost of extraction is 0. So what is it that we're really going to be looking for right now? We're going to be saying that, therefore, in the initial period, we're going to have this demand, 20 minus 0.4 Q, is going to be equal to the price, which is lambda. Because we said that the price is lambda when the marginal cost is 0. The marginal cost of extraction is 0. So this is what? This is the initial time period. The 0, the starting time period. Now, this is what you've got to become familiar with to understand what we are doing. It really isn't difficult. The difficulty is the first time you see it. It might not be very clear. So what is it that we're going to be doing right now? During the next period, what's going to happen during the next period? During the next period, what happens to rent? That's why all of these things build on each other. I hope, again, I cannot see you, but I hope that all of you recall that rent will increase every year by the interest rate. So during the next period, we're going to still have 20 minus 0.4 Q, but this is going to be equal to what? To lambda into 1 plus 1.1. Right? Let's assume, for the sake of argument, just to make it simple, that this is 10. If this was 10, then this will become what? 11. What about in the period after this? This will be 2 is equal to 20 minus 0.4 Q into lambda times 1.1 times 1.1, which means 1.1 squared. I hope right now that there's a pattern, and the pattern is sort of clear for all of you. But just in case it isn't, let's just do one more. So what we're going to find out right now, what in this next period, it's going to be 20 minus 0.4 Q is equal to lambda into 1.1 cubed. And then 1.1 to the power 4, 1.1 to the power 5, 1.1 to the power 6, and so on and so forth. So, given, therefore, an actual demand curve, remember the traditional demand curve is really expressed in terms of Q. So you can express this in terms of Q very easily, because it will become what? 0.4 Q is equal to 20 minus P. Therefore, Q is equal, you multiply them by what? 2.5. It becomes 2.5 P, and it will be 50 minus 2.5 P. So in that case, whenever you know, when Q is 0, you can really, what is the highest price that you're willing to pay in this case? When Q is 0. When Q is 0, how much is P? So P is 20, right? And then you can do the reverse. When the price is 0, what is the maximum quantity is going to be if you're going to draw a demand curve. So this will be, when P is 0, it will be 0.4 Q is equal to 20, therefore Q is going to be equal to 50. So this will be 50 and this will be 20. This will be the shape of the demand curve in this particular case. Right? Now, what we are saying is that, let's assume that we have a quantity of 200. How is it that we're going to allocate it over n period? What is that optimal allocation? Should we allocate it over 5 years, over 10 years, over 100 years? What is that optimal allocation? It is all a function of the shape of the demand, it is a function of the discount rate, and it's a function of the quantity that we think that we have. As all of these things change, then the allocation per period is going to change. I hope that this is clear, because what I want to do right now is solve one small example in details so that you will all be able to see it. And this will be really all what I want to do for this session. The second session, I'm going to show you the implication of this graphically, which is known as the optimum price path. Because notice that all what we're doing really is that we're determining what's going to be the price in every period. And so we will be able to guess what's going to be the price path of that particular issue. But then I want to introduce, as I told you before, a rather, I shouldn't say complicated, it looks complicated the first time you look at it. Again, it's really very straightforward, but a diagram that might look initially to be complicated concerning whether we should go ahead and what kind of a policy we should use when the price of oil really increases. Should we go ahead and tax old oil vis-a-vis new oil, which is what we have often done in the United States, which is totally wrong. So we have to resist the temptation of doing that. We've done it more than once, and it doesn't make sense. And environmentalists should know about this more than anybody else. So let's go back to this right now and see if I can give you a very simple example. What is the example that I just worked? I need my eyeglasses. Okay, here we are. So let me assume right now that I have a very simple demand curve. I'm going to even simplify it more. I'm going to say right now, my P is equal to 20 minus Q. I want to keep enough space so that I'll be able to show you some of the numbers. So, but I guess we can always erase it one more time. So let's assume that the interest rate, R or I, is 10%. It doesn't have to be, by the way, 10%. I find 10% the easiest thing to work around with, especially if you don't want to use a calculator. Because, you know, at 10% you can always do it very easily. So the 20 becomes 22, and the 22 becomes plus 2.2, and so on and so forth. So it becomes very easy to really calculate it by hand. And we're going to assume that the marginal cost of extraction is also 0. So what does that imply? That implies, one more time, let me spell it out. The price is always, and that's by the way, the value of the profiles that we went through last week. You're saying that the price is equal to the marginal extraction cost plus the rent. So if this is 0, therefore the price is equal to the rent only. So what are we going to assume over here? I'm going to assume that my quantity is 45. Yeah. So my supply is 45. If we're talking about oil, you have very reputable geologists that did some work for you, and they came to the conclusion that the total supply available that can be extracted is really 45, right? And you're assuming a marginal cost of extraction of 0, and you're assuming a discount rate of 10. So how is it that you're gonna proceed from here? You've got to choose a lambda. So that is the number one step. You choose a rent for the initial period. If you want to be more precise, call it lambda sub 0. So what is going to be my starting lambda? Okay. Assume that I'm going to start with a lambda of 5. What's going to happen right now to my initial period? So these are my time. So during the initial period of 0, what do I have right now? I have this demand curve, right, which is going to be this, whereby I'm saying that the price, so this is the quantity, and this is the price. I'm saying that the price is going to be what? 5, because there is no marginal cost. Notice the slight difficulty if you are to assume that the marginal cost is not 0. Let me assume that the marginal cost is 2. If the marginal cost is 2, and I am assuming that my lambda is 5, how much is going to be my price then? My price then would have to be the 2 plus 5, which will be 7. And that should also spell out why is it that we started by assuming that marginal cost is constant. So if you assume that it's 2, you're going to assume it's 2 during one period, then the next, and the next, and the next, and the next, and the next. Because if you assume that marginal cost is increasing, and you can, and we did assume that in the last profile, then that will complicate the calculations. So let's assume that there's a formula whereby the marginal cost increases from 2 to 3 to 4 to 5. Then the price will be the 2 or 3 or 4 or 5 in addition to the lambda. So it becomes a little bit more difficult to do the calculation. The simplest calculation will be when you assume that this is constant and it's 0. In that case, when the price is 5 in this particular case, how much is going to be the quantity? Take 2 seconds only. So 5 is equal to 20 minus Q. Therefore, Q is equal to 20 minus 5. So Q is 15. Right? I mean, this is very simple. What about right now the next period? Let's call it period 1. In the next period, what is it that's going to change? If you still recall what we have just erased, we said that lambda rent is going to become 5 times 1.1, because rent is going to increase at the discount rate. So over here, lambda which is the price, in this case, is going to be 5.5. Now, when lambda is 5.5, how much is the quantity? It's going to be 14.5. Let's take another 2 or 3 steps only, and I think in this case we have to, because I want to make sure that you've all following this, and you've got to be able to, let me stress it for the 5th, 6th time, you've got to be able to solve these. So now, what's happened to lambda? It's become 5.5 times 1.1, which becomes 6.05, right? You plug this in here, or by the way, you can plug it by doing the quantity equation. This will be Q is equal to 20 minus P. So if P is 6.05, how much is Q? Q is going to be 13.95. What about the third period? Now again, try to do it by yourself. I'll give you 10 seconds. This will be what? 6.05 times 1.1, which will become 6.655. What is going to become the quantity during this period is going to be 20 minus 6.605. It's going to be 13.345. 13.345. Now, one thing is very clear. What is going to be, by the way, the highest price over here? The highest price is when the quantity is 0. So your highest price is going to be 20. So ideally, by the time you get to 20, you want to have used your quantity of 45. Look, we're not even at 7, and yet we have exceeded it. That's how I know for a fact that this is wrong. Right? Let me give you a few seconds to think about this, because it's not totally spelled out in the book. The highest price that society is willing to pay is when the quantity is 0, right? You have your demand curve. When the quantity is 0, the price, the maximum price is going to be 20. And ideally, you want to use all your 45 by the time you get to that particular point. In this case, I have already exceeded my 45, right? And I'm not even at 7. So what does this mean? It means that my starting price is too low. So now, that's what I meant by guessing. It's what they call, by the way, those of you who've taken quantitative analysis, this is what they call an iterative procedure. So I take 5, it's wrong, it appears to be too low, so I've got to choose another one that's going to be higher. So probably what I will do next is to go ahead and use a lambda of 10. If I use a lambda of 10, you are going to find out that it will almost work out in this particular case. Now for an exam, since we're not using computers, we're not going to be able to get an exact number. I will be more than satisfied if you wind up with an approximation, but that is close enough, or at least you'll be able to explain what is it. So you'd have shown me, for example, in this case, that 5 is too low, and you say that the next one that I'm going to choose is going to be a lambda of 10. If you choose a lambda of 10, again, we're going to do the same thing, but let me make sure that one more time that you can follow it. So right now we're going to say that during the initial period, the first price is going to be 10, the starting point. When the price is 10, how much is going to be the quantity? Remember, oh, we've already erased it. Okay, let's put it here again. So quantity is equal to 20 minus P. So it's going to be, in this case, what? 10. Right? What's going to be the next price during the next period? Remember, for simplicity, we're assuming that this is 0, so the only thing that's going to change is rent, and rent increases by the discount rate, so this is going to become 11. When this is 11, how much is the quantity? It's 20 minus 11, which is 9. I go to another period. This is going to become what? 11 times 1.1, which is 12.1. The quantity is going to be 20 minus 12.1, which is 7.9. One more only. So this is going to be again 12.1 times 1.1, which will be 13.31. The quantity is 20 minus 13.31, which will be 6.69. 6.69. If you go through, where is it right now? 3, 4, 5, 6, 7. At the end of 7, here's 7. 7 will be almost 20, which will be 19, according to my calculation, almost 19.5. Let's just say 19.5 for simplicity's sake. And my quantity is going to be a half. This probably is going to be the correct answer, right? Or very close to the correct answer. Why? Because what is the maximum price? Remember, the maximum price is 20. Here we are. I want to right now, to make sure that this is applicable, all of these should add up almost to 45, right? So what we're going to find out right now is that these will add up to 45.6. So in this case, then, yes, the starting price is 10. So notice the starting price is 10, the next period is 11, the third period 12.1, 13.3, and so on and so on and so on. Now, the only other thing that's worth doing before I give you enough time to think about this, and then later on, as I said, I will add the other 2 graphs and a discussion regarding the procedure of what to do when we are encountering the probability, which we might, you never can tell since we've encountered it 2 or 3 times already, of having a tax on old oil vis-a-vis new oil. And we'll talk about that in greater detail. But I want to make sure that you understood this by doing something, not that is really complicated, but just to show you that as soon as you change it a little bit, what if I was going to say that price is equal to 40 minus 2Q? Remember, in the previous one, what did I say? I said that price is equal to 20 minus 2Q. In the previous one, I said that price is equal to 20 minus Q. If you plot these, more or less, you will find out that when the quantity is 0, the price is 20. When the quantity is 0, the price is 40. So this is one of them. This is the second one. And in both cases, you're going to find out that in this case, when the price is 0, the quantity is 20. And the same thing over here. So notice what you're doing right now. The slope of the demand curve is going to change. So now, even if you are to assume, by the way, that you have the same quantity, what was the quantity? We said that the supply was 45, right? So even if you are to have the same quantity and the same discount rate, so R is going to be 10%, we're going to find out that in this case, the allocation is going to be slightly different. I'm not going to go through all of it, but I did it. I'll just save you the trouble right now. I will find I started, the one that really works out will be when the price is 20, and what's going to be the price after that? 22, and then 24.2, and then 26.6, and then 29.2, and so on, right? What's the maximum price in this case? When the quantity is 0, the maximum price is 40. So my price should never go above 40. And I will get to 40 over here. What are the quantities? The quantities are going to be 10, 9, 7.9, 6.69, and so on and so forth. By the 7th period, I'm going to get almost here to 39 instead of 40. And by that, I would have used, I think, also 44 instead of 45, so that is close enough. If I want to be much more precise, then I will have to go ahead and change this to maybe 20 and a half. But then the calculation will become a little bit more difficult, so that is going to be acceptable. So notice, the same quantity, the same discount rate, different demand curves though, and therefore completely different prices. One of them is much steeper, so for the same quantity, we're willing to pay a much higher price. And even the number of periods is going to change in this case, but it didn't change a lot. It changed only by one period. If we are to introduce a completely different demand curve, we will obviously change all of this. So as you can see, one more time, and that is the tough part of this, is that you're saying that in the real world, if you are to be realistic, you assume, and that is the difficulty in the real world, is that the price is equal to the marginal cost of extraction plus the rent. You always assume that you know this, because you have a process of production and you know how much it costs you. Then you've got to estimate the rent, and that will determine the allocation of that particular quantity, given that this is either not going to change, or given that you have a formula for how is it that it is going to change over time, and given obviously that you know the quantity supplied at every particular point in time. I don't want to jump. I was going to talk about that later on, but we might as well mention it right now, and we'll mention it in the next session one more time. One of the problems, one can say very simply, that has created this energy problem that we're having right now with oil is the fact that around, say, 100 years ago when we started with oil, we obviously knew this, and it was pretty accurate. There's always a problem, by the way, in the marginal cost of extraction for an environmentalist, which is what? This really never takes into consideration the environmental damage. If you want this to be totally environmentally true, it must take into consideration the cost of externalities, also the damage that is caused. But let's forget about that for the time being. The problem is that we started with a very, very low rent. I know that you're too young to remember any of these things because you've never experienced them. However, up until the energy crisis for all practical purposes really started in the 1970s, in the early part of the 1970s, where a barrel of oil was selling for $11. And that was considered to be a big jump, because if you go back to the 60s, a barrel of oil was selling for $2. Why? Well, because we were really charging practically no rent. Had we had the foresight to see the environmental damage, and had we had the foresight to see the great big demand that's going to happen, therefore we would have charged a much higher rent. Had we started instead with 2, had we started with 20, then over here we would have been talking about 50, and right now we'd have been talking about, let's assume, 200. Then probably by now we would have already switched to a renewable. The reason that we haven't switched to a renewable is because of this. We started with a very, very low rent, actually with practically zero rent. I mean, that is the important lesson behind all of these things. So think about this a little bit. Spend some time trying to solve some of the problem. Write any kind of a demand curve that you want, and there's nothing really sacred about the quantity. Assume a quantity, assume a discount rate, and find out if you can solve it. And then, as I said, after a while, I will go ahead and share with you the couple of graphical representations.